So as I said, with this new formulation, it's much simpler to actually be able to prove a lot of conservation laws in a system of conservation laws. What is it? It didn't work. One way you think of it. What anymore? So I will talk about mimetic methods. So I will try to go fast. Then we talk about mimetic differences, which is one particular kind of mimetic methods. And then we'll do some explanation about what is a mimetic method, what it involves, and then some numerical examples of that considerations. Okay, so essentially we have two types of mimetic methods. One of them is the one that actually derive all the properties of the method. So what is a mimetic method? Mimetic method is a numerical method that not only cares about the accuracy, stability of the method, but also cares about conserving properties, symmetries of the solution, conservation of energy, conservation of mass, different conservation laws, different properties of the continuum. So the numerical method should be able to replicate in the discrete realm the properties in the continuum. And so you can see there are two types of methods. The ones that actually derive, what they do is try to approximate some integral theorem from vector calculus. For instance, they assume they want to approximate with high order of accuracy let's say the Gaussian relation theorem. And from there, they derive everything, all the operators. There are other, more recent methods that actually they try to replicate vector calculus, then tensor calculus, interior calculus, so any of these calculus, and from there, they construct the operators. Okay? So historically, we have seen this first method, the support operator method, actually developed in Los Alamos by Shaskov and his group. And then we have seen a method here in San Diego State, that's essentially working with Dr. Castillo. And then we have another group which is a collaboration between Los Alamos and a group in Italy. And there are some other researchers working in this. But I just want to focus on in the plethora of methods we are here. Okay. So a mimetic method actually works with a staggered grid. So suppose let's try to start explaining what it is in 1D. Suppose we have a dot interval, and suppose we have several cells of equal size, and then you will identify two different grids. The grid for the nodes or vertices of the cells, and also another grid for the centers. And so the collection of the two is the mesh. And so we have a grid that I denote xn, which is for nodes, and xc for centers. Okay? So we will have quantities living in these two different places. Okay. And so the operators that we plan to discretize are those familiar operators in vector calculus. Those are the divergence, so the divergence, the gradient. We will have some inner products that we will need for achieving high order accuracy for the Gaussian relation theorem. And we will have some interpolation operators when we go to higher dimensions. And because we have different sets, collections of points, we should move quantities from a collection of points to another collection of points with high order accuracy. And we have also the curl, the Laplacian, and a boundary operator. The main, why we are talking about this particular mimetic method. This method has a particular property, which achieves uniform degree of accuracy over the whole domain, not only in the interior, but also at the boundary and near the boundary. And this, as far as I know, is the only method that actually has that property. And before coming here, I did some work with mimetic method because of this property in particular, not because of the conservation law. So that, just keep in mind, this is a particular property that makes the method really special. Okay, so let's talk about very rapidly, the gradient and divergence. When you talk about the gradient, you actually apply the gradient to scalar fields. And when you talk about the divergence, you apply the divergence on vector fields. So the gradient you have the input of a gradient in the continuum. It's a scalar field, and the output is a vector field. And for the divergence, the input is a vector field, and the output is a scalar field. And so, for this reason, for others, we will actually assume that because of the gradient, we're able to compute the gradient on the boundary. Sometimes you have boundary conditions in a partial differential equation where the Neumann condition is given in terms of gradients. And so you need to compute the derivatives at these points. And also because of the definition of the divergence, the real definition of the divergence is an integral. It's the limit of an integral, of a quotient actually, of an integral, and the volume of the object is integrated. And so when you have that, you are not able to compute divergences on the boundaries. Okay? So for that reason, we will assume that the gradient actually has input at the centers and outputs at the nodes, and the divergence the other way around. So we will have a discrete operator, and when we try to see the matrix representation of this discrete operator, because there are different number of nodes and centers, this matrix won't be a square matrix. This won't be a square matrix, and this won't be a square matrix. And on the other hand, we introduce also an interpolator, which actually, so when you try to apply the gradient to a discrete function, you will need the function to be defined at the centers. And if you have the data for some reason at the nodes, you would like to move from the nodes to the centers. And for that, we have this operator, which is high order actually. So, and it has its mimetic properties. It's uniform over the whole domain. Normally, when they use interpolator operators, they lose accuracy on the boundaries. No, these don't. Okay, so we have gradient variance, and we have also the interpolation operator preparing data for G, and the interpolation operator preparing data for D, input data. Okay. So just to show an example of how this works, how could I achieve uniform accuracy over the whole domain? Suppose we are trying to get second order accuracy. You know, it's very easy to get. So if I want to compute the derivative here, and for a second order operator, I just need these two. Okay, and that happened to all of them. However, when I want to compute, when I want to compute the derivative here, I don't have two to use. So what I do is, well, I will use this, and the next one. So if I want to compute the derivative, I want second order derivative over here. I will use the derivative at 0 as a linear combination of data here, here, and here. Okay? So I have to determine A, B, and C. And what I do is I make an expansion in Taylor series. And then when you make the expansion and collect terms, you will have some terms using the the function at zero, the derivative at zero, the second derivative at zero. And over here I have the same. I have 0 times u of 0, u prime at 0, and u second 0 times 0 second. By matching coefficients, I get this relation. 3 equations, 3 unknowns, and I can solve it. I can find what are the weights. Okay? So this, and you can see how this works. Essentially, is that do I need to necessarily use these points? No, but this is the way, this is the way you see that you can actually compute uniform accuracy operators. Okay. So if I actually go back here, remember it is 8 over negative 8 over 3, 3, and negative 1 over 3. And so if I see the matrix representation of the gradient, you have those coefficients here. You are computing the derivative of the vertex on the left over here. Then for the second point here, and so on. And this is the last, and you see the coefficients reversed in order and in sign, because you are computing this in reference to this extreme and this other in reference to the other interval. So just symmetry, yes.
So Miguel, what is this different to doing just normal finite differencing left-hand sided or right-hand sided of that order? I don't remember what are the coefficients.
Normally you would use
the coefficients, not those. There are
not
no
those.
coefficients.
Are not those. Normally you will have lower order and using ghost cells sometimes.
So you can do any order. I can do left-handed differencing of any order that I
Yes,
want.
and it's artificial. It's not natural. This is inside the domain.
This is inside the domain.
The ones that I do are inside the domain as well. I just do left-handed on the right and I do right-handed on the left. They're still inside.
Yes, yes.
And I can do finite differences of second order everywhere.
You can.
And I do left-sided on the right. But look at second order and I do left-handed on the other side, and it's all second order. So I don't understand why you said that.
Look at
This is the only second order method everywhere.
well,
The finite differences I can do it. So, but there might be something that I don't understand because finite difference you can do second order everywhere as well.
Or higher. But the
Or
thing is
higher.
that this is natural. You don't do anything. You don't do hand, side, or he actually used a Taylor expansion. I actually don't. I consider the operator.
that's the way I going to say. This is a way of looking at the paper, but at the same time, you are probably using the information over here. Also, here is just using the centers. Okay, you see, you use only the centers and the information over here. Yes, Valerie.
I have a question. How do you get the h/3? Because I can see the h/2 and the 3 halves, but why you have the h/3 next to the V coefficient?
It's a typo. It's
Oh.
h/2.
Oh, okay.
Thank you. It's h/2. Yeah. So, yeah, that's why probably, yeah, I am not familiar with those methods. I haven't seen them.
But also this is not a dialogue. So you need to continue.
Yeah.
That will be offline and then,
But I want to show you how do you compute one of them.
or I can explain it to you in a piece of paper with all the details.
Okay, so essentially,
No, it's true.
you construct, yeah, but I wasn't aware of that. Probably, you can show me that. But I can imagine this. But being actually requiring that I need to use the sentence, probably something different. And for the base, I need to use the null information only. Okay, but the idea, I agree, is essentially the same if that's what you are talking about. Okay, so another example, this is a divergence 6 order operator. And as I said, the divergence is assumed to be 0 on the boundaries. So there is a row of zeros here, and this is 6th order. And so for the point that is next to the boundary, this is the stencil that you use to compute. For the next one is this one, and here begins for the interior points. They have 6 here. And so they go all the way, and then at the end, you have a replica of this in different order with the sign change, just to. Okay, so, and similarly, the 8th order gradient. So you have something like that. Okay, so you get the idea. Okay. So the matrix representation will be, sorry, this is not in the right place. So the matrix representation is this. I have my matrix, my gradient matrix, and I have the input. So the input is in the columns, and the output is on the rows. And this is the form that I will have for the general structure of the G. And just see the part that is related to the points that are on the boundary or near the boundary is here. And because of the anti-symmetry, this GR should be given by this, GL is over there, and R is the matrix that has one, not along the main diagonal, but the other diagonal, and the rest zeros. Similarly, for D, you will have a similar structure. You have the input on the nodes and the output on the centers. Okay, so I mentioned these mimetic operators. These two are checked. Okay, so is that we need? We need that the gradient, we know that the gradient of a constant is the vector 0. So that translated in the discrete version, the gradient of a constant, this is a vector of 1s, should be 0. Similarly, if I have a vector field that is constant, the divergence of that vector should be 0. And that means that the discrete version of this operation should be 0. So what that means? That means that all the rows, each row of G should add up to 0. The coefficients of each row should be 0. And also here. So we get 0 rows sums for D and G. And also that the first row and last row of the D's are 0. So I'm just collecting this because
I'm just gonna make a comment, Ricardo. You can have a function, okay, which is not a constant, and you use find the difference and you get 0. But the function is not a constant. Easily, you can construct an example. So it doesn't satisfy that property.
okay.
And there like this, there are many.
Okay, so now we want to, this is a method that actually is constructed from the Gauss divergence theorem, but the Gauss divergence theorem in 1D is the integration by parts formula, which is this. I just kept the notation in 3D, but you should see intervals from A to B instead of U. Okay, so the discrete analogs, because these are continuous quantities, I want to discretize, I will project the continuous scalar field and vector field into these constants. And these are the domains, the right domains on those. And I will introduce, so I want to actually satisfy this property in the discrete realm with high order accuracy. The only way to do that is to introduce some inner product weights, which are diagonal matrices with positive coefficients. So using this, so I know D and G, but I would like to find what are the weights. The only thing that I need to do is just by certain observations, observe that what I need to do is I need to solve this equation. It's a linear system of equations, and I will find the right coefficients for Q and the right coefficient for Y. So given D, I get Q, and given G, I get P. Okay, this seems to be interesting, but later you will see that this actually play a crucial role showing conservation. So again, the representation for the cube, you could demonstrate that this is the representation. It has ones from certain point to certain point, and then near to the boundary you have positive coefficients, and here the symmetric values. Okay. Similarly, you have a representation for P, the same characteristics.
And I assume that R and S are, if related to the order.
Exactly.
The higher order, they're going more.
Yes, exactly. I have a particular form for that, but I won't mention that because I am still working in the usual way of doing these things. Okay. So now we have two more checks. Okay, so let's try to make this.
Just wanna remind you that,
Yeah. How much time do we have?
you got 25 minutes.
Okay, so don't worry, you know your plan too. So there is an important thing. It turns out that Q and P are quadratures. Okay, in the sense that if I have a function G and I want to compute the integral on the integral of this in this interval, then if I make an approximation of this form using the P or the Q, actually I can prove that this is, so P and Q are actually quadratures if and only if they satisfy a series of relationships in terms of Betti numbers. Okay, but the question is, it doesn't, you are free to choose. You have too many solutions. You have less restrictions than unknowns. And so the problem is, how do you complete that set? And we didn't have before really procedure that works always. And it turns out that if you can actually reformulate this in terms of a linear programming problem using a convex polytype, and you could demonstrate that there are an infinite number of. But remember, what matters here is that P and Q are quadratures, which is essential. Okay. So extensions, we can extend these operators. I haven't mentioned anything about the curve, but the curve can easily be defined in terms of divergence or gradient. The Laplace is the divergence applied on the gradient, and the boundary is constructed in terms of this. So once you get this 4, you get the other 3 automatically. We are able to construct non-uniform versions because all of these assume that you have a grid that is uniform, and you can actually extend to Lorentzian structural bricks. So all of this extends very rapidly. And sorry. Okay, and the extended theorem, if you construct the discrete analog of this, will be something like that. And it's a little bit more complicated. I hide certain things because in 3D you see clearly quantities that are different places. They are in faces, in edges, and so you need to work with interpolations, and that justifies the introduction of interpolations. Also, the conditions that I mentioned before are constructed by interpolations, and also, if you want to prove vector calculus identities in the discrete sense, you will need those interpolations. Okay, so this is the way to introduce interpolations, and interpolations have this structure too. So I don't want to, you can imagine, and again, we just have this check too. And then, as I said, they have the other 3, and the other 3 actually follow. As I said, you can write the curve in terms of the divergence. L is D and G, and this is the way you actually create this boundary operator. So all of them are derived this way. One example, consider, so where I use this? I use these mimetic operations to approximate spatial partial derivative, spatial differential operators of PDEs. So suppose you have the Berger's equations, you have 2, this is a variable that has 2 components, and in vector terms, it is this equation. Remember, this is in 2D, so it has 2 components. And if I want to discretize that, I will introduce, I will actually project this into the grid, B1 into its grid, call this, so I reorder, because if you are working in 3D, you have to reorder these vectors and put as a column. Okay, and then you rewrite this in those terms. So it's like substituting all the differential operator by matrices. So you would substitute this by L and this by G. I need some interpolation operator to have the quantities in the right collection of points. And the way to avoid this kind of nonlinearities is introducing this diagonal. And so it's essentially the same. And I still need to, if I have boundary conditions, I still need to add the boundary conditions. And also I have a time derivative, and we have to do that. Something, we can use any of the time discretization schemes that exist for the time derivatives. However, you don't have to create all of this. You have seen that the result is complicated. We have a more library. It is the mimetic operators library enhanced. We have a library here at the university that is open source, and you can actually call these functions, and you don't have to worry about how to construct them. They are already constructed for you. So as I said, the beauty is, if I want to solve this applying finite difference, finite elements, well, I could just call these matrices, and I will just need to discretize this in time, and I will have an algebraic equation or a system. And maybe I need to iterate, or maybe not, depending on several reasons. It doesn't have time, maybe I need to iterate because it's a nonlinear elliptic equation. Because if it is, an implicit scheme, then I have to solve a system and choose a step. So, but essentially, we are just passing from the differential world to the algebraic world. That's, as I said, the previous approach. So what I mean for the previous approach is, in 2003, this method was introduced by Castillo and Brown, an initial flavor using certain amount, what I say, certain amount of points. They have a lot of freedom. And in 2017-18 was introduced by another method called Corvino-Castillo, which uses actually the minimum number of points that you need to get always. And so what you do is specify first D, G, and then from there Q, P, and the rest follows. In this new way of seeing things, is you don't, and from this you actually are able to demonstrate vector calculus identities and energy and mass conservation using essentially this fact that Q and P are quadrature. So that is a for conservation loss. This is crucial. And in the new framework, instead of specifying D and G, actually you just give the general structure. You don't need to specify the coefficients, and you will have a lot of freedom. So you have other methods, and no need to specify Q and P. You actually can have an infinite number of them. Okay, so I envision a software where you actually say, this is my G, this is my D, and it will give you all the other operators by itself. And actually, we're able to prove vector calculus identities. Energy, when I mean momentum, is first order, second order, third order, fourth order, any order of momentum. And for conservation loss using these Q and P quadratures, and also able to prove consistency, stability, and convergence. So you just need to give the relation, not the matrices, just the relation between them, and itself you will get all of this automatically. And that's the beauty of this. And so, let me see why. Oh, I made something. I think I made. I have. Oh, this is here. Okay. So this is one example. This is a simple example. These are the descriptions of the initial conditions. The velocity is a periodic domain. All the grids, and we are using for this particular equation fourth order Castillo, Corvino-Castillo operators. And for the time discretization, we are using a fifth order filter leapfrog with this value for the parameter. And this is a second order discretization in time. And you could see that the evolution. So initially you have this picture, and it starts to move and move along the way, and again you hit the initial picture. So this was prepared to run it a time just to perform a full cycle of this. And And here is a computation of the conservation of energy. And you see this riddle with some small quantities vary. And it's because I introduced what I need to have 5 steps in time. And I created those with using a forward Euler and twice leapfrog, just to get data to start. And that introduced those small variations. Here, we have another example. This is the 2D Euler example equations. We have, this is a system of conservation laws. We have 4 conservation laws in 2 dimensions. Okay? And you see rho is the density, u is the horizontal velocity, and v is the vertical velocity, and E is the total energy. These equations are close with this gas law, the ideal gas law, between the pressure and the density. And they depend on certain parameter that for atmospheric gases is taking usually to be 7 divided by 5. And well, I chose this because this is an elaborated system, and then we have the solution. We have the exact solution for that. If this is what it is, the domain is given by that. There are certain parameters specified: the initial velocity, initial position. What they are using is the 4th order Corvino-Castillo, 2nd order leapfrog scheme. And you see these pictures. And if you plot, actually, you see the conservation of energy of these quantities. And I think we have this other, you see the evolution of the conserved quantities in this particular case. I think it's the mass conservation, but you will have several same picture for all the momentums and energy. And this, I have to thank Dr. Johnny Corvino for the implementation of this example. And that's it. I think, yes, this is the last slide. So it's just to show that before we have the tools, but now we are able, I was not able to prove, you was trying to prove this preservation of energy and mass, and it took me a lot of time. And then once you realize that you don't need to worry about what is inside the matrix, but its structure and its properties, from there you can actually prove all these conservation laws. And it was easier for me to see without focusing too much on the actual values of the entries of the matrix. And this is all what I have. Thank you.
I have plenty of questions, but I'm gonna go for a beer, so I can ask you later. I need the opportunity to the others.
So questions?
So how efficient are these mimetic difference operators compared to like just normal finite difference?
Like, in terms of the speed and what we have, the library we have implemented actually implements all the matrices as how we call it, sparse matrices, and it has been proven to be really fast. For instance, probably you're familiar with Jared Krasinski. He actually solved Navier stocks in a much more complicated geometry. It was the deep canyon that is in Monterey. And so he was able to prove that actually when he parallelized the whole thing, he gets better efficiency than the ideal efficiency, because the way he solves certain linear systems, which are the most expensive part of the computation. Instead of using normally any method, he uses super LU, because he observed that the right-hand side is the only thing changing. So when you use LU decomposition, you already store L and U, and you don't need to reconstruct and iterate on that matrix.
There was another question he asked. he asked, would you compare this with finite difference? The complexity, the computational complexity is the same,
Yes, is what I.
but it is at least one order of magnitude more precise or accurate than finite.
And this is
Sometimes two.
This is, by the way, we got, the group here, got, NSF grant for actually trying to transition, the more library into an ecosystem that is more stable. So for that, we were interviewing people about, users and potential users of this library. And what we observed personally was that any person that used finite difference with finite volume that was able to use the library will have the same statement. Is mimetic method is better than finite difference. They were able to solve problems that they weren't able to solve. So as a general comment, it's something that we observe.
So can I ask a follow-up question? I think I was reading in, I don't know whose paper, but that you had implemented it also C++ as well.
The library is implemented in Octave and in C++. So the work that Jared did was fully in C++.
So there's like an interface for that if you want to use it?
Yes. You should be able to download it.
Communication is important. What do you mean by an interface?
I mean, so that you can interface within like C++, you don't have to like use them intermediately.
This is a library, you write your code. For example, C or C++ code, and then you invoke the library version in C++. Now you use MATLAB, there is one MATLAB Octave, which you can just program your code with MATLAB, but instead of 300 lines or more, it will be like 10. That's a big difference.
So you just call the functions in the library, like any other library.
We do have a lot of reports that whoever is interested, just you can send an email to him, to me, and we can give you how to use the library and also reports that students have done, and some are published in the CSRC repository, and some have been submitted to journals. Yeah. And we're looking for collaborators and hopefully developers.
Yeah, and even though I guess a good portion of you have already taken COM 670, which is where we have a seminar about mimetic methods. So we explain mimetic methods, and then each student actually works on a project. It's a need. And they have to submit a report, and if they are able to solve all the issues, then we were able to actually publish those reports. And some of the work actually will become journal articles later. So in the next semester, there will be a course that is mimetic methods. It's essentially what I have said, but more with all the details, and focusing probably using more. So how do you download it, fork it, and how do you actually use it? And it will be great. We need people, students, essentially, that are willing to help with the coding of the library itself.
Contributors.
Developers.
How to deal with non-homogeneous boundary conditions?
Where we were having actually in general, because what I described in the example, I didn't mention. So let me. I think it's this one. Okay, it's not. I am not assuming homogeneous. I am assuming, here I said just that I just focus on the partial differential equation without the initial conditions or the boundary conditions. If you have to do that, you have to actually add those. Usually, you would do infinite differences. You have to tweak the matrix. However, we have those functionalities in the library. You have normal boundary conditions for one and Dirichlet. And actually recently added the mixed periodic, and we will plan to incorporate periodic boundary conditions too. So you just call, but you need to know also true infinite differences. So when you discretize, you have a linear system. The linear system has two parts: the matrix, which is essentially this part, and this, and then you have a right-hand side. On the right-hand side, this boundary condition will show up over there. So you need to somehow indicate, but where that goes if your boundary conditions are fancy. But if one of these, you just use the boundary conditions that are as utilities.
And just a follow-up, so in the same similar way, you can specify different boundary conditions on a subset of cell centers or faces of the
Yes,
image?
now it is implemented. It was recently added, maybe a couple of months ago. So we have the mixed derivatives by pieces. Yes.
The development of the low library, because now you have all the operators implemented. So what kind of development you are assuming right now? Just curious.
Oh, we need to improve, or we have a little bit of unbalanced library because it is much more developed in Octave and MATLAB than in C++. We need to improve, for instance, on what I mentioned, there is this Corvino Castillo operators, which are the ones that are right now in the library. There is people that start working in theoretical aspects of the mimetic methods using the first method, and they don't have a software because the software, the machine that has the software just collapsed and not have it anymore. And so, essentially, what I said is, right now is we can do the following. You specify your gradient operator and your derivation operator, and the library should be able by itself to construct the rest. That is a part that is not here. Okay? And this is something that we came up just recently. So we should improve the library. It's getting behind, and we have much more theoretical. So for instance, checking errors, stability, consistency. There is testing, writing tests for the library. You have to test all the operators, all the examples. So there is a lot of work actually. And if you're interested, just let us know.
Whoever is interested, just say so in an email. And we'll talk about possibilities. On that note, we're gonna thank our speaker one more time.